Hello and welcome back to Introduction to General Relativity. In the previous lecture, we started modeling the universe with Einstein's general theory of relativity. After some symmetry arguments, we arrived at the following form of a highly idealized metric for the universe. The goal of today's lecture is to derive all the geometric quantities we need to solve Einstein's field equation, and then solve Einstein's field equation for this particular form of the metric, this FLRW form. So this is the FLRW metric, and our goal is to derive from the metric today everything we need to solve Einstein's field equation. So what does that mean? That means the Riemann tensor, Ricci scalar, Ricci tensor, and we'll also need to talk about the stress energy tensor as well. So given this metric, it's a exercise for you how about I do the flat case first and then the non-flat case? So it's an exercise for you to show the following Christoffel symbols. So first we'll deal with the case k equals 0. That's the one that corresponds to Minkowski space. Well, not Minkowski, sorry. Flat space like time-like slices. So the case k equals 0. So in that case, we could write the metric as, well, basically a rescaled normal Lorentz metric. We just go back to Cartesian style coordinates for this Euclidean slice coordinate system. And then in this coordinate system, the non-vanishing Christoffel symbols, you can work them out pretty easily. So this is an exercise, although honestly it's not that difficult an exercise. So here's I'm only going to write down the Christoffel symbols that don't vanish. And all the rest actually vanish. So here, a with a dot over it means the derivative with respect to tau, proper time. And you have a whole bunch of other Christoffel symbols that are non-vanishing, but they're all very symmetric on account of the fact that the metric itself is rather symmetric. So this is tau's and z's look very close to each other here. Okay, and from that you can go ahead and work out the Riemann tensor and the Ricci scalar and Ricci tensor. We're not going to focus so much on this Euclidean sliced coordinate system so much. In fact, I want to express everything in as general way as possible that can capture the basic elements of the universe we live in. So now, for that purpose, we need to look at the k is not equal 0 case. And in this case, you can derive the Christoffel symbols again, but we're going to use this spherical coordinate system to derive the Christoffel symbols in this case. And we'll have the following rather long list of Christoffel symbols. I mean, any individual Christoffel symbol here isn't that difficult to derive. Probably the biggest challenge you're going to face in doing this calculation is ensuring that the inevitable mistakes that creep in, that you detect them quick enough. And having said that, I may have made mistakes as well, although I have checked these results. But nevertheless, I may make transcription errors. so it's important to not entirely trust what I write here. So you get this long list of Christoffel symbols like this. I admit I've checked a couple in Mathematica. And indeed, although I do believe it's important to be able to do these kind of calculations yourself, there reaches a point where something like Mathematica is really a first-class tool to prevent mistakes. Okay, we're almost through here. Oops. And we're down to the last two Christoffel symbols now. Alright, so when we're given the metric here, this FLRW metric with this particular coordinate system with spherical type coordinates, and we have this parameter k, oops, I forgot to remind you about k equals -1, that's the hyperboloid case. K equals 0 is the flat case, flat spatial case. Oops. And k equals +1 is the spherical case. So you have three representative metrics to capture the three kinds of space-time that are isotropic and homogeneous. And given this metric, you can write it as a matrix if you wish, or just keep track of all the components. You can go ahead and just use the formula that we introduced many lectures ago for the Christoffel symbols, and you can go and calculate the Christoffel symbols. And you should, with any luck, if I didn't make a transcription error, and if you didn't make any errors, you should arrive at this list of Christoffel symbols. And now, after that, we're not done, right? The Christoffel symbols do contain all the information you do need to write out Einstein's field equations, but of course Einstein's field equations pertain to the Ricci tensor, or rather more directly to the Einstein tensor. So we need to work out the Ricci tensor and therefore the Einstein tensor. So here we go again, more calculations later. Long list of components for this tensor. So these calculations you cannot find in Wold. You have to, in Wold's textbook, he doesn't really cover the case where k is non-zero, which is a bit of a shame. But then again, the textbook was written before we understood that the universe is expanding and the expansion is accelerating. Which is a pretty amazing result. Okay, so here's the non-zero components for the Ricci tensor. Note that there's only a handful of non-zero ones and that the Ricci tensor is diagonal. And here's the Ricci scalar. If you go ahead and just add up, take the trace of that thing above. Remember, when you take the trace, you have to use the inverse of the metric in there somewhere. So that's why this takes this form here. And now we've got almost enough stuff to write out the Einstein tensor. So let's now write out the Einstein tensor. So there's a g tau tau term. This is again an exercise for you to confirm these. I mean, I did these calculations myself, it really didn't take so long. And then the next two more components, there's a theta theta component. and there's a phi component. And now we have enough information to write out Einstein's field equations. We have the stress energy tensor. Remember, we discussed that form of the stress energy tensor for an isotropic and homogeneous universe in the previous lecture. And we also exploited those symmetries to write out Einstein's field equations in a much simpler form, and we arrived at really two independent equations that we need to worry about. And so let's write it out. So here they are, GAB plus lambda, the cosmological constant, times by the metric, little gab, is got to equal 8 pi TAB. And we can either use the result from the previous lecture, or more directly, which is what I'll just do here, is look at some various components of this equation, and we'll actually be able to quickly identify the independent equations. So if you look at the TT component, or the tau component, and substitute in the Ricci tensor, Einstein tensor, blah 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 that I just derived, then you arrive at the following equation, which we'll call 1 prime. And if you look at the RR component, then, well, a little calculation later. Including cosmological constant here. Would lead us to the second equation. Of course, there are several more components, but none of those lead to independent equations after these two. And we'll call this one II prime. So these are two equations, and you can just go ahead and solve them if you want. 1 prime and 2 prime. That's totally fine. You can do it. But you can make your life a touch simpler by combining these equations in various ways, differentiating them and eliminating common terms. And when you do so, you will find that those equations 1 prime and 2 prime are equivalent to the following equations, which we will make reference to as a little later when we solve these. But before we go ahead and solve these equations, we're going to note that this cosmological constant term, lambda, can be eliminated. And the way it gets eliminated it gives you a sense of how, of what role the lambda, the cosmological constant term, plays. So let's make this the following substitution. Rho gets mapped to rho plus lambda over 8 pi, and p gets mapped to p minus lambda over 8 pi. So if you make that substitution, actually you can eliminate lambda. In this way we can actually interpret the cosmological constant. We can interpret it as representing a form of energy with a negative pressure. And this pressure is not only negative, it's equal in magnitude to its energy density. That means that little p equals minus rho for this form of energy. This energy has a name. It's called dark energy. And there have been several independent surveys of this hypothetical dark energy, and so far we haven't been able to reject the hypothesis that dark energy is present in our universe and dominating, in fact, or playing a dominating role in the late stage evolution of our universe. And that is, so the discussion up to this point about eliminating lambda is just to allow us to eliminate lambda from the equations. So we've got these equations 1' and 2' here. Lambda's inside it, but we can make this particular substitution, and then we can end up with some equations which don't feature lambda anymore. But now we have to bear in mind that pressure can go negative. Or we must allow for the pressure to go negative in order to accommodate the presence of dark energy. So these are the two equations that we're going to use to model the evolution of our universe. And we'll call these 1 and 2. And just by looking at these equations, we can actually deduce a fair number of interesting observations about the evolution of various types of universe. So there's one case that you might think is highly relevant for the universe we find ourselves in, but in the end, of course, has been rejected by the latest observations. You might imagine that in our universe, rho, the energy density, is positive, and P, the pressure, is also non-negative, right? You might imagine that. And then in that case, so this does not, to repeat, this does not actually apply to the universe that we live in. As far as we know now, P, there is the cosmological constant term that does feature a negative pressure contribution. But what if we just assume, that rho is strictly greater than 0 and P is non-negative? Well, we can actually deduce a couple of quite interesting observations. Namely, that the universe, in this particular case, cannot be static. Because a double dot is strictly less than 0. So if you take a look at the equation 2, and you look at the right-hand side, well, you see that rho and P are non-negative, so the right-hand side is strictly negative. A itself is positive, so that tells us that a double dot is strictly negative. And what does that mean? Well, the universe must always be contracting or expanding. Right? Because that means that a dot has to be strictly greater than 0, or a dot has to be strictly less than 0. A dot can't be 0, Otherwise a double dot would be 0, right? So the universe is either always expanding or contracting, except in the case where this cosmological constant term happens to just balance out the contribution from the cosmological constant term, just balances out the energy density. And indeed, that was the original motivation that for Einstein to introduce the cosmological constant. Now, of course, later observations confirmed rejected the hypothesis that the universe is static, and so somewhat melodramatically, this is considered a mistake. But of course, with hindsight, now we understand that the way you should do physics is you should include all terms that are allowed by the symmetries of your theory, and the cosmological constant term is allowed by the symmetries of your theory. It's one constant term, and it's non-zero as far as we're aware in our universe. So I find it a bit melodramatic to depict the cosmological constant as a mistake of Einstein. This is really the motivation may have been it may not have been courageous enough, but the principle that you add in all the terms that are allowed by the symmetries of your theory is a good principle, and one that you should follow when formulating physical theories. You shouldn't set any coupling constant or interaction term in your theory to 0 unless you have a good reason to do so based on experimental evidence. Now, when you think that the universe is expanding, maybe you sort of think of there being a distinguished point where expansion is happening around it, perhaps. You shouldn't really think of the universe like that. You should rather think of galaxies as being distributed like on the surface of a balloon, and that the universe is sort of blowing up the balloon, or the balloon is shrinking. And that means that all the distances between isotropic observers, there's no preferred center, right? We already know that, and that the distances are all sort of symmetrically changing between isotropic observers. So let's actually think about or study the distances between isotropic observers and see how they're changing in one of these solutions. So imagine we have two isotropic observers, a distance capital R apart. And that's at some proper time t, or some constant tau, sorry. So let's just study how the distance between two isotropic observers changes as tau changes. Well, firstly, the change in this distance r is, per definition, right, it's dr d tau. That's how it changes. But that's equal to r on a times dA d tau, which is, per definition, something called h times r. Now, to get the second line here, you have to note that the metric is changing with tau, and that the distance between two isotropic observers is being rescaled as tau changes, right? And a is the scaling factor. And so what we've done here is we've introduced something called h, which is irritatingly called Hubble's constant, although it's not constant. It's Hubble's function. So let's put a scare quote here. It's not constant. And so what we learn is that the change in the distance between two isotropic observers is somehow proportional, or instantaneously proportional, to the distance between the observers, right? It's basically exponential separation. And what does that tell us? Well, if r is large enough, then easily, right, v can exceed the speed of light. But that's bad, right? Things aren't allowed to travel at faster than the speed of light. Well, actually, that's not true in general relativity. You've got to be a little bit more careful about how you state the speed of light, and the speed of light is a limit on velocities. This actually entails no particular violation, this observation of relativity, because in general relativity, all that we required is that locally measured relative velocities at a single event does not exceed the speed of light. Global relative velocities such as v, you see the distance between two isotropic observers is this global distance quantity that's determined by a geodesic. But there's no such restriction on those velocities. And actually, you've seen in the exercises, I've mentioned that de Sitter as an idealized, de Sitter universe as an idealized solution of Einstein's field equations. It features exactly this. So this is no violation of relativity. Because in general relativity, only locally measured relative velocities so locally means infinitesimally close observers at a single event do not exceed the speed of light. Global relative velocities such as v are not so constrained. And indeed, we do observe this. So I've alluded to it several times and stated it directly several times. The universe is expanding. You can look at the redshifts of various galaxies and you can confirm that the universe is expanding. So given that the universe is expanding, a dot is bigger than 0, what do we know? Well, we know that a double dot is less than 0. So what does that tell us? Well, that tells us that the universe must have been accelerating at a faster and faster rate as tau goes in the negative direction. And this is true even with the cosmological constant term there, in the cases that are relevant for us. All right, has to be, right? The universe, a double dot is strictly negative. The only way this is consistent is if everything was accelerating faster and faster and faster and faster as tau goes negative. Even at constant expansion, forget the fact that it actually was accelerating, even at constant expansion, then at a time t given by a dot divided by a, which is like the inverse of this Hubble constant, which isn't a constant, we would learn, and this only gets worse when you include the fact that we weren't actually in a constantly expanding universe, that we learn that a is 0. At this time t. Now that's a singular state, right? the metric has the spatial contribution to the metric has an a in front of it. And if a is 0, then that means the distances between all events at that instant of time is 0. Zero, right? All events in the universe at that instant t are at the same location. And hence, if there's any energy density or matter density present at that point, well, it would be infinite. And so this has been given a name, right? This is called the Big Bang. That instant where the universe comes into being and all matter or energy density in the universe is concentrated on a singular point, and then the universe after that instant commences expansion. But I want to emphasize that this is not an explosion of pre-existing matter. There was no before t. So there was no time, the universe simply didn't exist, there was no matter, there was nothing before t, big T. And the reason is that it is impossible to extend the space-time manifold in a non-singular way or connected way. I mean, this is not, people have studied this endlessly, and there's a variety of different things that could really have happened in the real universe. However, theorems on singularities in the Lorentzian manifolds pretty much force us into the conclusion that the universe did commence somehow in a Big Bang scenario, and that there was nothing present before this Big Bang. This, of course, can be endlessly debated, but as we find out more observational evidence and as we learn about the dynamics of our universe, this does seem to be the most economical hypothesis. All right, that's it for this lecture. We've covered essentially a qualitative discussion of the equations governing the evolution of a homogeneous and isotropic universe. And in the next lecture, we will look at the quantitative solution of equations 1 and 2. We'll solve them, or at least I'll write down the solutions. And then we will move on to the final canonical topic of this lecture series, namely the Schwarzschild solution. But that's it for now. Thank you very much and goodbye.